So we started with single variable, then we came to x and y. We started talking about equations. We started talking about linear equations like x is equals to 5 or y is equals to 6, or even the two variable thing, two variables linear equation, something like 2x plus 3y is equals to 5. So these things we were doing, and then we proceeded to even solve quadratic equations, something like ax square plus bx plus c eventually equals to 0. So when people were solving this, they were having some issues by solving it. Uh, and but the real problem started when they were actually solving the quadratic equations. So even a simple equation like x cubed equals to 1, when they were solving, they were able to find only one root, which is x is equals to 1. And if you look at this x cube is equals to 1 in detail, what you'll get is x cube minus 1 is equals to 1. And then when you factorize it, basically this is nothing but aq minus bq. So it will come as x a minus b into a square plus ab, basically, and plus b square is equals to 0. So x cube minus 1, you factorize it, you will get this. This is fine, right? When you factorize x cube minus 1, you will get x minus 1 into x square plus x plus 1. Why? Because we know that a cube minus b cube is nothing but a minus b into a square plus ab plus b square. So with this, we used to get, okay, x minus 1 is equals to 0. One is that. And then next one was x square plus x plus 1 is equals to 0. We used to get x is equals to 1. And then when you were, this was a quadratic equation. And when you solve it, you will get x is equals to minus b plus minus b square is 1 square minus 4ac, 4 into 1 divided by 2. That would be nothing but minus 1 plus minus square root of minus 3 divided by 2. So they, I mean, very invariably they will start getting something like this, that square root of minus 5, square root of minus 10, or things like that. And whenever these people who were solving such equation encounter such a problem, they will say that such a solution doesn't exist, and they will just leave it at that. Solution doesn't exist, and they will leave it at that. And they basically, we started defining something like, this part was d, right? Discriminant, right? B square minus b4ac is discriminant. And we used to say that whenever it is greater than equal to 0, roots are real. I mean, eventually we started saying that when they started defining what is real, what is imaginary, and when started saying that when b square minus 4ac is less than 0, then roots are going to be imaginary. Okay, something like this was introduced to counter whatever problem they were facing here. That whenever they were getting an entity inside a square bracket, a square, sorry, square root, and it was a negative quantity, they were saying that in such a case, they defined it like the roots would be imaginary. And this story started from here itself. So someone figured out, as in, like, whatever is coming like this, right? Minus root 3 or minus root 5 or minus root 7 or something. They started saying that, can we write minus root 3 as root 3 into square root of minus 1? Can I write square root of minus 5 as square root of 5 into square root of minus 1? Can I write the square root of minus 7 as square root of 7 into square root of minus 1? So they started saying, okay, anything under the square root and which is a negative, I can just simply convert it into one positive quantity, which we already know how to solve it, and something which is square root of minus 1, which we still don't know how to solve it. So someone came up and said that, okay, let's call this square root of minus 1 as I, and then we will call it minus 1. So this is how the definition of iota started. I is equals to, basically I is called iota, and this is this value of I is equals to square root of minus 1. And they started saying that, okay, whenever you encounter a square root and then there's a negative quantity, start writing square root of 3 and I. We will write it like this. The square root of minus 5 will be written as square root of 5 and I, and square root of minus 7 will be written as square root of 7 and I into I. So initially I wasn't called an imaginary thing, but rather it was called a lateral number, and we will come to that as in why it was called a lateral number. Uh, but uh, this is how basically they arrived at something and defined something like I is equals to square root of minus 1. And just to conclude this story here is this: x cube is equals to 1. We know that any polynomial of n degree will have n roots. So here when we were getting only one root, it was not actually able to substantiate that lemma when we were saying that any polynomial of n degree will have n roots. But using this, when we had x minus 1 is equals to 0 and x square plus x plus 1 is equals to 0, now we started saying that okay, there are two other roots which are not real but kind of imaginary, and we started calling okay, so now this is one root and then there are two imaginary roots, so there will be three roots. So then it was substantiated that okay, any polynomial of n degree will have n roots, right? So similarly, 2-degree polynomial will have two roots, and degree polynomial. So 3-degree polynomial will have three roots, and degree polynomial will have n roots. Okay, this is a fundamental principle or fundamental theorem of algebra. Just do that once again. I know that you guys know. So I into I would be basically square root of minus 1 into square root of minus 1, which is going to be minus 1. So I square is going to be 1 minus 1. IQ is going to be minus I square. uh, I I square into I basically. Now we know that I square is minus 1 and I, so this is going to be minus I, and I to the power 4 is going to be I cube into I. So I have got minus I into I is going to be minus I square. This is going to be minus 1 into minus 1, so it's equals to 1. Similarly, if you keep on going, I to the power 5 is going to be I to the power 4 into I, which is going to be simply 1 into I. This is going to be I, and I to the power 6 is going to be similar. I to the power 5 into I, so it's going to be I square, is going to be minus 1, and I to the power 10 is going to be I, and I to the power 8 is going to be 1. Right? So basically this is going to be minus I. So we see that there is a pattern evolving. I know that you guys know it. Just reminding you that I and every fourth power, when you add it, it will, the pattern will repeat. I square will be equal to I to the power 6. I cube will be equal to I to the power 7, and I to the power 4 will be equal to I to the power 8. And essentially any power of I with multiple of 4, k would be always equal to 1. So using this, if someone is asking you to calculate the value of 2057, I to the power 2057, what you will get is I, and then get it in terms of fourth power of I. So this will be 4 into 5, 1, and then it will be 4. So when I multiply 514 with 4, I will get 6, 4, 5, and then 2056, and then I can write it as plus 1. So I can also write it as 4 into 514 into I to the power 1. I know that any I power of I with multiple of 4 will be 1. So this is 1 into I. So this is going to be I. So this is how you solve any power of I. I hope this part you guys know. I'm just doing it again just to ensure that you guys understand. Now again, coming back to the problem, or rather uh, statement which I made. So why it was called a lateral number, not an imaginary number in the beginning, is this. Oops. So we know that if I have to represent real numbers, I represent it on a real number line, something like 0, 1, 2, 3, 4, 5, positive set, and this set will be negative minus 1, minus 2, minus 3, minus 4, and minus 5. So when they looked at this I, so they said that it actually exists laterally. It exists laterally to the number real number line. So this real number line is having numbers like this going like this, but this is your basically lateral axis. You can call it lateral axis also right now, and this is your real axis. So when you have I over here, what will happen is that you will have I over here. Now when you multiply I with I, we saw that I square is going to be -1. So this will come here when you multiply I. Then you again multiply it with another I. Then I'll come here and it will be -I. And I will be able to come here. Then you multiply it with another I. Then it will become 1. And then again you multiply with another I, it will again become I. So basically this imaginary number or whatever with I is, actually it actually remains either on this axis, or it just keeps on going around whenever you are multiplying this number with I itself. So they say that they said that this number is actually existing laterally to the real number line. That is why they were calling it a lateral number, not imaginary number in the beginning. But later on, the name imaginary gained currency, and we started calling I as an imaginary number, because I was equal to the square root of -1. But that is why it is also called a lateral number, because it exists laterally to the real number line. Okay, so I is existing here or here, which is lateral to the real number line, which is this number line. Okay, now once we have understood the imaginary number, now the real definition of complex number starts. So any number which is represented in form of a plus ib is called a complex number. This is called a complex number, where a and b are real numbers. So any number like 2 plus 3i would be a complex number, or minus root 2 also, plus or minus of root 3i also will be a complex number. Even for that matter, cos theta plus I sin theta would also be a complex number, because cos theta will value of cos theta will be between -1 to 1, and sin theta's value will be between -1 to 1. So any number wherein this number and this number is the real number, and there is a basically multiplication of I in the next part, then this number of this form is called a complex number. So with that, even a number like 1 is also complex number, wherein I can write 1 as 1 plus 0 I. So such a complex number has got its imaginary part as 0. All right. So before that, I have to define what is real, what is imaginary. So A is actually called the real part of the complex number, and B is called the imaginary part of the complex number. So any number, real number is also a complex number whose imaginary part is 0. In this case, imaginary part of this complex number is 0. Okay. Similarly,
Okay.
there can be a purely imaginary number whose real part would be 0. So 0 plus I, this is a pure imaginary number. This complex number is a pure imaginary number, because its real part is 0. So with this definition, you can understand, as in now, until now we understood that real number encompasses all sorts of number, but now complex number is going to encompass even the real number. So now the hierarchy or the tree would be like this: complex number, then under that there will be real number, under that there could be rational and irrational number. Under rational numbers, we can have integers. We can as well have natural numbers. We can have whole numbers and all those. So what essentially I was trying to tell you is that now complex number is a superset under which all these numbers are there. So since real number encompasses all other numbers, now complex number is encompassing even real number, because real number is type of a complex number whose imaginary part is zero. So with this, what we can understand is we can also write z as real part of z plus I times imaginary part of z. So this real z is what? Real part of z is a, and imaginary part of z is b. Okay. So now it's a new number as we mentioned. So until now we understood real number and we understood various different things of real numbers, as in how to add, how to subtract and all that, right? Now we'll also understand how to add, subtract, multiply, divide the complex numbers as well, right? But prior to that, there is another thing which we need to understand. If we say that there are two complex numbers which are equal, right? If I say z1 is equals to z2, it can only happen when real part of z1 is equal to real part of z2, and imaginary part of z1 is equal to imaginary part of z2. So what I mean is, say z1 is a1 plus ib1 and z2 is a2 plus ib2, then a1 has to be equal to a2 and b1 has to be equal to b2. So this is something we need to remember, because there may be questions around it. As in, if I say there are no two complex numbers are equal, then this has to happen. And we will see that essentially this is same thing as the ordered pair, because we can plot these complex numbers in Argand plane or imaginary plane, as we call it, or complex plane. So we will see that this is actually essentially ordered pair AB. That is why in ordered pair case also we say, right, that A, if AB is equals to XY, in this case it can only happen when A is equals to X and B is equals to Y. This happens in case of ordered pair. Got it? So yeah, this is another thing which I wanted to mention. Now coming to the part wherein how to understand, there are rules around subtraction, multiplication, addition, and all that, right? This is something which we need to understand. So there are rules around it. So I'll first of all I'll define as to how to add or subtract. So addition of complex number. So how do we do that? So we define addition of complex number. So say you have got z1 is equals to a1 plus ib1, and you've got z2 is equals to a2 plus ib2. Then if I have to do z1 plus z2, then what we do is we separately add the real part a1 plus a2, and we separately add the imaginary part b1 plus b2, and then put I. So this is how we define the addition of complex number, that adding the real part separately and the complex part separately. So this is how we define. Similarly, even the subtraction of complex number. How do we define subtraction of complex number? Subtraction of complex number z1 minus z2 is defined as a1 minus a2. Basically, you have to subtract the real part separately and the imaginary part separately. Okay. Now with this, there are certain rules which we need to know how to go about doing addition or subtraction. So there are some rules. So I'll just keep mentioning the rules quickly, and then maybe you guys can let me know if you are clear or not. So the first one is called the closure law. Closure law says that if you add two complex number, then the result will be also a complex number. So, so I'm not going to write it. So basically what they are meaning is if you have got Z1 and Z2, when you add Z1 plus Z2, it's also complex number. So you guys can see that this part is, I can write it as more like A, and then I can write this more like B. So this is Z1 plus Z2 is nothing but A plus IB, and we know that any number which can be represented in real part plus I times real part, basically A. So this can be called a complex number. So this is first law is called closure law, that when you add to complex number, the resultant number will be also a complex number, right? So you might be wondering, as in like say, let's say one number is, let's say my Z1 is A1 minus IB1, and my Z2 is say again A1 plus IB1. If I add Z1 plus Z2, I will be left with A1 plus A2, right? And is this the complex number? Yes, it's the complex number because its imaginary part is 0. So any real number is also complex number. So that's the reason that when you add to complex number, you will always get a complex number. Alright. So this is the first law. Then there is second law is the commutative law. Commutative law, as we know, that this law says that Z1 plus Z2 is going to be equal to Z2 plus Z1. So in what order these complex numbers are, it doesn't matter because essentially the result will be same. The third one is the associative law. What is this associative law? Is that if you have got three complex number, so in which order you add will not matter. So Z1 plus Z2 plus Z3 will still be equal to Z1 plus Z2 plus Z3. So here you will be adding Z1 plus Z2 first and then adding Z3 later. Here you are adding Z2 plus Z3 first and Z1 later. So intermediate quantity would be changing, but the final result would be same. It is as I mean all these things are following real numbers law. For example, here also it is nothing but 2 plus 3 is equals to 3 plus 2. Or here it is also say 2 plus 3 plus 4 is equals to 2 plus 3 plus 4. So when you do this, what you will get is 2 plus 7 first. Here you will get 5 plus 4. So the intermediate quantities are different, but the final result is still 9. This is also 9. This is what here as well in associative law. So in intermediate steps might be different, but the final result would be same. After associative law, there is a law or the rule called existence of additive identity. What essentially it means that there is an existence of a zero basically. So what it means that if you add a complex number to 0 plus 0 I basically, then you will get a z only. So this is essentially an existence of zero, which is a additive entity. So it says that in terms of rules that there will be an existence of a complex number to which if you add another complex number, the resultant number will be the same complex number. This is what is the existence of additive identity. Or in other words, it says that there is an existence of zero basically as like real number. When you add 2 plus 0, you will get the 2, or you can add anything like minus 3 also. When you add to 0, you will get minus. Same way, when you add 0 plus 0 I to any complex number, you will get the same complex number. And then the final law says that existence of additive inverse. What it means essentially is that existence of a negative quantity. So basically it says that for every z, there will be uh, additive inverse which will exist, uh, basically which will be nothing but minus z. So call it z1, and basically addition of both of this will be 0. So z1 is nothing but actually minus z. It is essentially same as having 2, and for every 2 there will be a minus 2 which will be equal to 0, or for every 3 there will be a minus 3 which is equal to 0, or in other words it's just like on a real number line. If there is a 1 here, there will be minus 1 here, there is 2 here, there is minus 2 here, or even there is like minus 2.5 here, there is 2.5 here. So there is an inverse, additive inverse exists, and if we add both of them we will end up at 0 is what it says. So why we are defining such laws is because this is a new number and we have to have rules whenever we encounter such a thing as in like add or subtract or divide. We have to follow certain rules, and that's why these rules are there. After defining addition, we have to define subtraction, how to subtract. So actually subtraction is easy to understand because as we know that just like real number, all these rules don't exist for subtraction. So for example, what I mean is that commutative law, as I was mentioning, that 2 plus 3 is equals to 3 plus 2 does not exist for 2 minus 3 is equals to 3 minus 2. We know that, right? It is not equal. 2 minus 3 is going to be minus 1 and 3 minus 2 is going to be 1, right? So we know that for subtraction such rules don't exist. So what we define for subtraction is that, say you have a complex number z1 which is a1 plus ib1, and you have another complex number which is a2 plus ib2, and you have to do z1 minus z2, right? I can essentially write this as z1 plus minus of z2. What I mean here is that it is going to be a1 plus ib1, and this minus z2 is going to be minus a2 plus ib2, minus a2 minus ib2. And once I have this as plus here, all the rules which I have learned for addition will apply here. So same way, so for example, z1 minus z2 I was saying, right? Now commutative law will be applicable here because z1 plus minus z2 will be equal to minus of z2 plus z1. So you guys can see that the commutative law is applicable because that this is these two things are equal. If I have to write it, right, z1 plus minus z2, which I was writing. So here what I have written, I have written a1 plus ib1 minus a2 minus ib2. On the other side, since minus z2 is in the beginning, I will write minus a2 minus ib2 plus a1 plus ib1. This side also it will be a1 minus a2 plus I times b1 minus b2. This side also it will be a1 minus a2 plus I times b1 minus b2. So what it actually is saying here is that whenever you are encountering subtraction, rather than convert it into addition by converting the other complex number into a negative complex number, and then apply the formula, whatever, apply the rules what you know about the addition. So for subtraction we will not understand any rules or other read any rules, because all the rules of addition will apply to it once I convert the other number minus z2 to another complex number minus z2. Now coming to multiplication, so let's define multiplication. So how do we do a multiplication? So you've got another one complex number which is a1 plus ib1, another complex number a2 plus ib2. When you are multiplying z1 into z2, what you will get is a1 plus ib1 into a2 plus ib2. Similarly, it will be a1 into a2 plus ib1 a2 plus I a1 b2 plus I square b1 b2. I square b1 into b2. Now we know that I square is minus 1, so I'll just write a1 a2 minus b1 b2 plus I times a1 b2 plus b1 a2. Now this is also basically real number, this is also a real number. So this is essentially again in the form of a plus ib. But the important thing is that how do you multiply? It is simple, that you multiply first with second, first with first, second with first, second with second, and then you will get the result. Once you know that how it is done, you know that what you need to do to get the real part is first you multiply this with this with this, and then put a negative sign, and then multiply this with the other one, and this with the other one, and then have the I sign. Anyway, if you don't know the rule, just multiply one with another one as we multiply. So this is how we multiply, simply one to another. And again, there are rules. Again, going to be same rules for some of the rules. So closure law will be applicable here, and which we have seen that if you multiply one complex number with another complex number, you will end up with another complex number, and which is true. So this is what is a closure law. Then commutative law is also applicable here. Commutative law. So commutative law says either you do z1 into z2 or you do z2 into z1. It will be same, right? You guys can see that, right? If we have a2 plus I b2 into a1 plus I b1, I will end up with the same result, which will be a1 a2 minus b1 b2 plus I times a1 b2 plus b1 a2. So z1 z2 will be equal to z2 z1. This is commutative law. Associative law will also be applicable here, which will be nothing but we have z1 into z2 and third complex number z3, or we multiply it like z1 first, sorry, z2 and z3 first and z1 later. It will not change. I'm not going to prove it, but you guys, if you want, just take three complex number and try it. You will end up with the same result. So this is what is associative law. Fourth is called the law of multiplicative identity. So it says that there will be a complex number which will be existing. If I multiply that complex number with another complex number, I'll end up with the same complex number. So z into, if I have 1 plus 0 I, then I will be end up with z itself. So it is essentially talking about existence of 1. So we know that if you multiply any number with 1, will end up with the same number, is what it is trying to tell you here by this law of multiplicative identity. Same way, we know that law of multiplicative inverse. So essentially it says that for every complex number, there will be existing another complex number. When you multiply it, you will end up with 1. So basically z2 is going to be 1 by z, and z2 is represented as z inverse also. So basically every number will have its own inverse. It's just as simple as what we have for real number. Like for 3, there will be 1 by 3 existing, for which it will be 1. For every minus 3, there will be minus 1 by 3 existing, using which you will be getting 1. So this is what is the law of multiplicative inverse. And final law is basically, it's called distributive law, which is very important. We have to know this. So distributive law is basically, if you have z1 and here it's a multiplication and inside it is z1 z2 plus z3, then it is simply a multiplication distribution of z1 over z2 and z3. It will be z1 into z2 plus z1 into z3, which is also we know for our own real number, like 2 into 3 plus 4 will be equal to 2 into 3 plus 2 into 4. So same law is applicable here as well, that z1 into z2 and z1 into z3. So z1 is basically distributed over z2 and z3. It's called, that's why it's called distributive law. Now, since we have understood all the laws related to multiplication, for division also, the same laws will be applicable only when you convert the other complex number into. So basically, what is the division? Division is going to be z1 by z2, right? Now z1 by z2 can be also written as z1 into 1 upon z2, and we know that if such 1 by z2 is also complex number. So basically whatever law is applicable for multiplication will be now applicable for this number. So for division also we don't need to know anything. We just apply the law of multiplication here as well. Okay. Now with this there are some identities in a way, or you just have to know that whatever uh, formulas which we knew for our real number will be applicable here. So what I mean here is that we know that, right, a minus b whole square is a square minus 2ab plus b square. We also know that a plus b whole square is going to be a square plus 2ab plus b square, or we know that a plus b whole cube would be a cube plus 3ab, a plus b, and then b cube. So similarly, for every complex number, these things will be applicable. So z1 minus z2 whole square would be z2 square. Similarly, z1 plus z2 whole square would be equal to z1 square plus 2 z1 z2 plus z2 square, and z1 plus z2 whole cube would be also equal to z1 cube plus 3 z1 z2 z1 plus z2 plus z2 cube. Okay, so all these are applicable here as well. So whatever you know about real numbers would be applicable for complex number also most of the time. Okay, there is only one exception which we will talk about later. Uh, Other than that, whatever rules we follow for real number would be applicable here for complex number as well. All right, so you have to solve this. What is this complex number? So this complex number is nothing but z is we going to be minus 4 minus I, and if you have to represent it in this format, then you will represent z1 as minus 4 comma minus 1. Okay, so this is what they have done, minus 4 minus I. Okay, this is fine. Now let's talk about, write the multiplicative inverse of 3 comma 4. They are asking you to write the multiplicative inverse of 3 comma 4. So first of all, you have to write what is my z is. So z is 3 plus 4i. And what is my multiplicative inverse? So basically what we said, that for any z there will be z1 existing. When you multiply it, you will get 1. So z1 is what? Z1 is 1 upon z. So 1 upon 3 plus I, 3 plus 4i. Whenever you get such a thing, right, you multiply it with a conjugate of it, which you'll come to know later. But right now what we'll do is we'll multiply it by 3 minus 4i, 3 minus 4i in numerator and denominator. So we'll get 3 minus 4i, and here it will be a plus b into a minus b, which will be a square. So 9 minus 4 square I square, a square minus b square. Okay, so top part it was 3 minus 4i, and bottom it becomes 9 plus 16. So finally my complex number is going to be what? It is going to be 3 by 25 minus 4 by 25i. So this is what is the multiplicative inverse of 3 comma 4. Okay, so this is simple multiplication, and once you multiply as we did last time, so you know that it will come in form of a plus ib, and this is what a plus ib would be. So market that they are talking about a plus ib. So every time you write a complex number, you have to write it in real part and imaginary part. In some cases, when you have uh, only real part, then you write 0i, so that the imaginary part is looking like 0, but it is also in the form of complex number. Okay. Conjugate and modulus are not taught today, but for example, write the multiplicative inverse of I to the power minus 35. They're saying write the multiplicative inverse of. So first of all, you have to get that complex number, then only you can write the multiplicative inverse of it. So So the question is here, write the multiplicative inverse of I to the power minus 35. This is basically I to the power minus 35. First of all, you have to solve I to the power minus 35. So what is I to the power minus 35? I to the power minus 35 is going to be 1 upon I to the power 35. So I can write it as I and divided by I to the power 36. Why did it? Because I to the power 36 is going to be 1. Why? Because I and I to the power 36 is going to be 4 into 9. It's going to be in terms of power of 4. So that is why it's going to be I by 1. So that is why I multiplied top and bottom with I here. So basically what I did is I by I. So that's why I got I to the power 36. So now we've got is I, right? So this is basically a complex number Z, wherein my real part is 0 and imaginary part is 1. 1 into I. So this is my complex number. And I have to write the multiplicative inverse of this. So multiplicative inverse of this is basically Z inverse as I did last time. And it's going to be 1 by Z. And 1 by Z is going to be 1 by nothing but 1 by I, and 1 by I can again write it as like, okay, let's do it in two steps. So this is 1 by I, and 1 by I can write again I divided by I square. I am just multiplied it with I in numerator and denominator. So I square is going to be minus 1. So I got minus I, right? So this is the multiplicative inverse of I to the power minus 35.